Problem 443. A boy weighing 400 newtons jumps from a height of 2 meters to the ground below. Assume that the force of the ground on his feet is constant. A. Compute the force of the ground on his feet if he jumps stiff-legged. The ground compresses 2 centimeters and the compression of tissue and bone is negligible. Okay, so to start things off here, we are going to calculate the velocity of the boy just before he hits the ground. And so in order to do that, let me draw a coordinate system, and just like a sketch. So here is the boy. This is 2 meters. And of course he's displacing himself downwards. And we can put a coordinate system like this, y, and we'd like to find the velocity just before he hits the ground. So once I find that velocity, I can find what the net force on him is from his acceleration, because I know that he stops in 2 centimeters, and then I can use the kinematic equation without time to calculate the acceleration, and from that the net force. And then from that I can figure out what the force of the ground on his feet is. Okay, so the velocity just before hitting the ground is going to be derivable from Vy squared equals Vy naught squared plus 2 a sub y times delta y. So in other words, that's going to be equal to 0 meter per second squared plus 2 times minus 9.8 meters per second times displacement of minus 2 meters with the coordinate system that I've chosen. Vy is equal to the plus or minus the square root of this. The square root of this turns out to be 6.26 meters per second. And of course, we choose the minus sign because it's downwards. So that's the velocity he has just before hitting the ground. And now we can use that as the initial velocity during the segment in which this last 2 centimeters here, this is 2 centimeters, in which he decelerates, and of course during that leg of the trip his acceleration is that way. So in order to figure that out, I can now use this equation again, except this equation right here. I can use this equation again, but now his final velocity is 0. His initial velocity is minus 6.26 meters per second squared plus 2 a sub y times minus 0.02 meters. This is the 2 centimeters. Okay, so notice a couple things here. First of all, the negative here disappears inside the square root, and secondly, that the minus for 0.02 meter displacement has to be a negative sign because of my coordinate system. Y is in the up direction and this displacement is in the down direction. And then thirdly, that this is an equation where AY is the only unknown, so I can solve for AY. Okay, so if I solve for AY, A sub y is then equal to 6.26 meters per second, the quantity squared, divided by 2 times 0.02 meters, and that comes out to be 9.8 times 10 to the 2 meters per second. That's a huge acceleration. It's basically 100 Gs. So now, when he hits the ground, there's going to be a weight force that he has downwards like this, and there's going to be a force of the ground upwards on him during this leg of the trip. We can call that N. And this is going to be bigger than that, which is going to lead to this acceleration, which is going to be in the upward direction, in such a direction anti-parallel to his velocity that he slows down. And so I can now use Newton number 2, and I can say the net force upwards, N minus W, is equal to the his mass times the acceleration. And I've already solved for the acceleration. So N in that case, which is what A is asking for, is ma plus W. And so in other words, that's equal to ma plus mg. His weight is his mass times the acceleration of gravity, which is equal to m times a plus g. You have to calculate his mass in order to figure out what this is. His mass we can get because we know his weight is 400 newtons, and if we divide that by g, 9.8 meters per second per second. This is his mass, excuse me. His mass is 40.82 kgs. So just to repeat, his weight divided by g is the mass that he has here. And so that now goes in here, and N is then equal to 40.82 kilograms. That coming from here, times the sum of the acceleration that I computed up above here, 9.8 times 10 to the 2 plus g, 9.8 meters per second per second. And if we compute that out, N, the force of the ground on him, is 4.04 times 10 to the 4th newtons. Okay, so to put this in perspective, if we take this N and we divide it by his weight, I get roughly 4 times 10 to the 4 over 4 times 10 to the 2. Let me put an approximate sign here. And so you can see this ratio is 100, which is to say that the force exerted by the ground upwards on his feet is 100 times his weight. That's a very large force. Okay, that's A right there. Put A like this. Excuse me. And B now asks to compute the force his legs exert on his upper body, which weigh 2.5 times 10 to the 2 newtons under the conditions it's assumed below. Well, essentially we're just looking at his upper half, not his whole mass. And so the lower part of his body is going to exert a force on the upper part of his body. However, the upper part of his body is accelerating at the same rate as the lower part of his body. So we can say ma is equal to FL minus W, and this now is the force of the legs on the upper part of the body. And the M here is the mass of the upper part of the body, and the W here is the weight of the upper part of the body. So maybe I should put a little sub U on both of these here. And so if I solve for F sub L, I'm going to get MA, M sub UA, same A that I had before, plus W sub U, which is M sub U times A plus G, because M sub U times G is W sub U. And that's exactly the same expression I got for N over here, if you look at it, except I have M sub U here instead of M, and so therefore I can say that this is going to be the same as the previous upward force I calculated, 4.04 times 10 to the 4th newtons, times the ratio of the masses. Okay, so on the top, I'm going to have ratio of the weights, excuse me, same difference. 250 newtons on the top and 400 newtons on the bottom, because that ratio will then correct for the smaller mass that I have here. And that calculation now indicates that F sub L is 2.52 times 10 to the 4th newtons. And so if you take the ratio of that over his initial weight like we did up above here, just to give you some feeling for how big that is, F sub L over W turns out to be 63. Somewhat smaller than 100, but still very sizable. So it's still a very large force. Okay, part number C now says, say that he bends his knees on impact and stops his downward motion in 40 centimeters instead of the 20 centimeters that was originally used for both parts A and B. Okay, so the idea here is the distance stopped is 20 times greater, and from this this equation right here, this now will be 20 times as big, which means the acceleration will be 20 times less. And so that means that the force, since the acceleration is 20 times less, the force will be 20 times, roughly 20 times as big. And so what I can say then is that the new acceleration is equal to the old acceleration, which was 9.8 times 10 to the 2 meters per second squared divided by 20. Okay, so that turns out to be 449 meters per second. And then if I recompute F sub L, which is what they're asking us to do, so F sub L is equal to mu times this new A, this A here, plus the weight of his upper body, and that is going to be equal to his mass, the mass of his upper body times the acceleration that we computed back here, plus G. Okay, so that turns out to be 25.51 kilograms times 49 meters per second plus 9.8 meters per second, and that computes out to be 1.50 times 10 to the 3rd newtons. In terms of a ratio with its weight, this F sub L is a little bit less than 4 times his weight. Much more manageable, much less likely to lead to any fractured bones, broken ankles, etc.